Hello. This is my third video about tides, and it's quite a short one. The first one we learnt about how tidal forces cause the oceans to slosh around the place. In the second one, we learnt how tidal forces can slow satellites down, slow moons down, so they stop spinning. In this one, something much more dramatic happens. We start pulling things to shreds. So in the previous video, we looked at how to calculate tidal forces, and we concluded, well, let's cut to the chase. There's an inverse cube law here. So tidal forces get stronger as you move towards the sun, say, faster than gravitational forces. So if you stand here on the Earth as it currently is, the tidal force on you is about a 10 millionth of your weight, which means that if you got 200 times closer to the sun, that's pretty hot and it's pretty uncomfortable. It's not actually inside the sun, it's in an orbit around the sun. Well, 200 cubed is getting on for 10 million, so the tidal force is comparable with your weight. And if you got closer still, you'd actually get plucked off the Earth altogether. So there's a thing called the Roche limit. So if an object gets too close to something really massive like the sun or Jupiter, bits get plucked off the surface, is what I've written it. It's often said that, it's often written as if an object is held together only by its own gravity, then it'll get pulled apart if it gets too close to something like Jupiter. Now you can work out how close that is, and it turns out it depends on the density of the objects, not on their size. That's for a given massive object like Jupiter. Now think about comets as a thing, as a group. So comets are made of ice, basically. They all have roughly the same density. So it makes sense to talk about a Roche limit for comets around any given body, like Jupiter or Saturn. And so if a comet gets inside there, it's going to get pulled apart if it's only held together by its own gravity. But of course it will be, because if it gets anywhere close to the Roche limit, it's going to get violently distorted by the tidal forces and it'll crack. It's made of ice, right? So then it'll be in lumps, which will get pulled apart. So that's not just theory. Here's Saturn. It really happens. Look, I'm going to draw around Saturn roughly where I think the Roche limit for comets is. So what's all those rings? Well, in all probability, once upon a time, there were a couple of comets, or there was a comet or two there, and they got pulled apart into bits. And then the big bits got pulled into little bits, and the little bits into tiny bits, and the tiny bits into gravelly bits, and so there we are, tiny little things in orbit around Saturn. And they're not going to join together anytime soon because they're inside the Roche limit. Now that's not the only example. Here's a pretty one. What happened here? So this is an impact crater on Ganymede, which is one of the moons of Jupiter. So, well, in all probability, what happened is that something, probably a comet, got too close to something else, probably Jupiter, and got pulled apart. If you do the sums, you see they do actually get pulled apart into straight lines like this. And then a little while later, it's smashed into Ganymede. Isn't that remarkable? We knew there were straight lines like that in the solar system. Which brings me on to the story of Shoemaker-Levy 9. Shoemaker-Levy 9 is a comet. Well, it was. Shoemaker-Levy were actually three people, a pair of Shoemakers and a Levy, and they discovered this comet in 1993. And when a decent-sized telescope was turned on it, this is what it saw. Well, if that isn't a comet that's been pulled apart by tidal forces fairly recently, I don't know what it is. Well, it is. So the question is, when was it pulled apart? That's not too hard to work out, is it? Because once you've got a decent fix on it, you can see how fast these parts are moving apart and run the video backwards, as it were, and see when they came apart. And the answer was the previous year. And then you can also, once you've got a good fix on the orbit, work out where it was when that happened. And the answer was it was amazingly close to Jupiter. So it was at this point in a ridiculous orbit about Jupiter, an orbit with an eccentricity of 0.999. Now, what on earth does that look like? Well, here's an ellipse of an eccentricity of 0.99. There's the focus. So that's where Jupiter was, if you like. I've blown that end bit up. There's the focus. Ridiculous, isn't it? So how did it get there? Well, like most comets, it was in orbit around the sun, and it was in an orbit that got out as far as fairly elliptical orbit, out as far as Jupiter and into probably somewhere near Mars or something. And it got very close to the orbit of Jupiter. So it was inevitable that sooner or later it would get very close to Jupiter itself, and then Jupiter captured it. Actually, capturing a comet is a quite subtle thing, if you think about it a bit, because if a comet gets very close to, say, Jupiter, well, it's either in an elliptical orbit or a hyperbolic orbit. If it's in an elliptical orbit, then it's not being captured, it's always been there. And if it's in a hyperbolic orbit, well, it's going to disappear. You actually need a third body involved to effect capture like this, and that, in this case, it was the sun. So here's this comet coming out from the sun as far away from the sun as it's going to get, and it gets really quite slow. It comes out here, it gets really quite slow, and along comes Jupiter and sort of sucks it out of its orbit, and it more or less dropped onto Jupiter, and there it is. So it got captured sometime in the 20th century. Right, now then, the other thing you can do once you've got a good fix on its orbit is work out what's going to happen to it. And the answer was it was going to hit Jupiter next time round. So all eyes on Jupiter, except that unfortunately it was going to hit the far side of Jupiter, so no human eyes could see it. But this, Galileo could. It turns out Galileo was on its way out to Jupiter, just the right timing, and this is it. This is one of the bits hitting Jupiter over a period of 7 seconds. One of the things that's remarkable about Jupiter is that its day is only about 10 hours long. It spins amazingly fast. So in fact, this crash site was visible from the Earth within a few minutes, and there was a great fireball, and here it is. So that's the fireball that was caused by one of the bits of Shoemaker-Levy 9 hitting Jupiter, and these are some of the previous bits. They hit over a period of a few days. Just for context, there's the Earth on the same scale. It's fun, isn't it? So tidal forces can do more than sloshing water around.